Hello and welcome. Today I want to talk about light. In this video, I'm going to share what I've learned about the radiation we all enjoy. But first, a quick PSA for my few returning viewers. Yes, you too. I like you very much, so keep on going. And I said you too, I literally mean you 1 and 2. Just to give you an insight, this is the second time I'm recording this video. After I stopped editing the first version, because I realized I write my scripts as if I'm a scientist or a teacher, or like I'm some sort of authority in the subject of astronomy. And I'm not. My approach going forward will be sharing newly acquired knowledge with a side of commentary and opinions. It will be obvious to the educated viewer that I may not grasp some of the concept, and that's okay. All I ask is provide your own opinion on the subject of the video by leaving a comment to challenge me, or tell me if you actually learned something new. Believe me, I'll appreciate your feedback. And with that out of the way, let's get into it. I think it's safe to say that sunlight is a fundamental source of energy. It sustains most life form on Earth. It also helps maintain the ecosystem in our home planet. This can be an organic or technological ecosystem. I also learned light is an instrument for detecting molecular composition of an object. And this last part is the focus of this video. And to start it up, the first question we need to ask, what is light? So light is simply radiation composed of photons. Photons are pretty much packets containing both waves and particles. Photons can travel in a vacuum at the speed of light, which is 300,000 kilometers a second. The speed of light is a universal constant, which is a set amount or quantity of anything that can't be explained by theory. It just is. Natural light, specifically sunlight, is a primordial form of energy. For life in general, sunlight is responsible for providing a livable ecosystem. It also improves perception and interaction in an environment. So basically, it allows you to see, move in a room, touch, be able to identify what you're touching. For humans specifically, sunlight is a source of vitamin D. It can also regulate sleep cycles. It also improves mood along with immune functions. In science, light is used for research. It allows for better understanding of the environment. Spectroscopy, I will talk about that a little bit further in the video, but that's very important. And it also allows us to study the universe since the dawn of cosmology. Artificial light also plays an important role in our modern existence. It enhances visibility in the absence of sunlight. It also improves productivity and aesthetics. The list goes on and on and on. So I had an idea about everything I've mentioned so far, but I needed to dig deeper in the scientific aspect of light. For starters, I wanted to understand why we see light. Obviously, the question, what is the light we see, came to mind. The light we see, or simply visible light, is an electromagnetic radiation. It's visible because it can be perceived or detected by the human eye. Visible light is composed of different wavelengths. When interacting with an object, light is absorbed or reflected, allowing us to distinguish the colors of an object. So because I needed material for this video in particular, I went back to study light. And I learned that Isaac Newton was into alchemy. He was an alchemist. Isaac Newton, the highly influential English physicist, mathematician, astronomer, and theologian. Theologian? He was a priest too? That's his profile by Wikipedia. That guy was an alchemist. But no judgment, I'm just surprised, that's all. So in the 17th century, Newton experimented with sunlight and prisms and revealed that white light was a part of a spectrum. He demonstrated that light was composed of 7 colors. Think of the rainbow. Visible light is made up of wavelengths represented by a color. These colors put together creates clear white light. A reminder that Isaac Newton identified these colors and coined the term spectrum in his book Optics. Our eyes contains cone-shaped cells called photoreceptors. These photoreceptors act as receivers, detecting light wavelengths. I mentioned earlier that light can either be absorbed or reflected. And this is due to the molecules in an object, which is how we can distinguish the color of any object. But I'll get back to wavelength a bit further in the video. I also had a basic understanding of light benefit for Earth ecosystem. What is new to me is the concept of the visible light spectrum is part of the electromagnetic spectrum. So we are a bit further in the video, and as promised, let's talk about visible light wavelengths. What I understand is that visible light have wavelengths ranging from 380 to 750 nanometers. The visible light contains 7 colors, each corresponding to a wavelength range. In your screen, you can see the wavelength range for each of the colors, but is that all? Or are we short-sighted? I mentioned that the visible light spectrum is part of a larger spectrum, the electromagnetic spectrum, composed of light radiations or wavelengths that are either lower than violet, 380 nanometers, and higher than red, or higher than 750 nanometers. In 1800, German astronomer William Herschel, using Newton's technique, conducted a light experiment with a prism and a thermometer. He was able to measure the temperatures of each color of the visible spectrum. He noticed an increase in temperature between blue and red, and another increase in temperature was detected beyond red. He effectively discovered infrared light, used in night vision cameras and motion sensors for security alarms. It doesn't stop there. Additional discovery of light radiation took place in the 19th century. And I mean that throughout the entire century, there was a particular light radiation that was discovered here and there. So far, we've mentioned the discovery of visible light in 1666 by Isaac Newton, using a prism to separate light. The discovery of infrared in 1800 by William Herschel, also with a prism, but adding a thermometer to measure each color's temperature. Then ultraviolet in 1801 was discovered by Johann Wilhelm Ritter. Ultraviolet is what causes skin damage and cancer. It keeps sunblock companies in business for a generation. These people are rich, you hear me? Radio waves in 1887 by Heinrich? I want to say it's Heinrich Hertz, used for radio and TV signals, wireless communications, and more. Microwaves in 1888 by James Clerk, using math equations. Microwave is used in satellite communications, mobile phone networks, and the appliance to heat up your food. Yeah, the microwave you have in your kitchen, it uses microwaves in order to heat up the water molecules inside of any food to heat it up. They discovered how to do that. That's crazy to me. I digress. The discovery of X-rays in 1895 by Willem Röntgen or Röntgen, I'm not sure how to pronounce that name. X-rays are used in medical imaging to visualize bones and internal organs. You know, if you break a bone and the doctor wants to see how bad the damage is, they use X-rays to pretty much look inside your bones and see how did you mess up. And last but really not least, gamma rays was discovered in 1900 by Paul Villard or Paul Villard. Gamma rays are used in cancer treatment and sterilization of medical equipment. And what I've learned is that visible light is a spectrum inside of a bigger spectrum. Like I said, most people, and I want to say the majority of people that are able to see, that have vision, can understand the visible light spectrum in a way. Me included, we may not be able to grasp the entirety of the visible light spectrum, but we can detect it with our sight senses. We can have an idea how it works. So some part of the wavelengths are absorbed or some of them are reflected. It's where it goes a little bit too technical. It's not as easy to grasp. But the visible light and all the other radiations that I've spoken so far, together they make the electromagnetic spectrum, the bigger spectrum. This radiation can also be considered as light. Yes, they are also considered as light. It's just that we, again, humans associate light to things we can see. But light, as long as it has photons that move at the speed of light, it is light. Even if you can't see it, it's just absorbed. We don't have the senses, we don't have the ability or the organs, the appropriate organs in order to see anything that is outside of the visible spectrum. Those wavelengths our photoreceptor cells can't detect, and therefore we can see them. All this radiation, they all travel at the constant speed of light. But why am I talking about light anyway? The answer? Spectroscopy. So ever since I got into cosmology, astronomy, and whatnot, one thing that got my attention was how can scientists recognize the molecular composition of distant stars, galaxies, even planets? A regular lens telescope sitting under our atmosphere, and remember the atmosphere creates like a layer, like an additional filter to go through. It allows us to reveal maybe the size, shape, and structure of matter in space. We'll be able to actually see the planet, kind of make up the shape and the size, and maybe the structure as well. But the lens telescope don't allow us to see what gas said object contains. I don't know if I see a gassy planet, yeah, a gassy planet, let's say Jupiter, I won't be able to know what type of gas dominate said planet using a lens telescope. It's impossible. Spectroscopy is the study of light interaction with matter. As far as I can understand, in space, information travels using light. Think of radio waves allowing for communication. Like, for example, transmitting data from the International Space Station to Earth and vice versa. It uses radio waves, right? Or let's say infrared. Infrared can detect thermal information from an object whose visible light is blocked by matter that is in front of it. So imagine that there is this huge cloud of gas, right? and there is a star behind it. But this huge cloud of gas blocks the star that is behind it. If you use an infrared instrument, you'll be able to see that star behind it because it goes through the matter that the dust is actually made of. The thing that I find interesting about spectroscopy is that light in itself contains information embedded in it, which is how we get information from faraway objects in space. Objects that are billions of light years away in the cosmos. That's a huge distance. Oh, hi and welcome. I just realized that I should have added this part explaining what a light year is. While editing, I was trying to see if I could quickly find some sort of image explaining and going over the details of a light year, and I couldn't. So I found this video in one of the NASA's YouTube channel. This one is called NASA Solar System. But basically this explains and illustrates what a light year is. So this is the Milky Way. And as you can see, the size or distance across the entire Milky Way galaxy is 100,000 light years. So basically, light year is the distance light travels in 1 year. Imagine you have a flashlight and you turn it on. Normally, when you turn a flashlight on, the radiation of light will appear instantly. Relative to us, it's immediate. But when you turn on a flashlight in a vacuum or just in space in general, we can also take, let's say, a star. Let's say the light of our sun, right? If we want to calculate how much it will travel in a vacuum that is 100 light years across, it will take a long time. The light you see of the sun is 8 minutes old, which means what you're seeing, the sun that you're seeing right now, it's what happened 8 minutes ago. If, and I hope not, but if there is an explosion, if the sun goes supernova right now, the moment you see it, that means that the supernova already happened 8 minutes ago. So again, the definition of a light year is the distance light travels in 1 year. And as a reminder, light travels at 300,000 kilometers per second. So each second, light travels 300,000 kilometers. So let me start up this video. So the Milky Way, 100,000 light years across. Light time is the distance light travels within a specific period of time. That's the example of the sun. So if you see all the particle radiation, well, that's an animation, right? Those radiation will take, from the moment it leaves the sun to the moment it reaches, it takes 8 minutes. Let's continue. That's 1 light second. In 1 second, light travels 300,000 kilometers. 1 light minute. See where Earth is located compared to the sun? The line right now that you see from the sun here to here, that's just 1 light minute, right? To Earth is 8.3 light minutes. This is pretty much what I just saying. So for light, when it leaves the sun to reach Earth, the region of Earth, the orbit of Earth, it takes 8.3 minutes. Let's continue. To Jupiter, it takes 43.2 light minutes. To Neptune, the sunlight takes 4.1 light hours to reach Neptune. 1 light day equals 25.9 billion kilometers. And this is 1 light year. This is the scale, what 1 light year is, right? Which equals to 9.4 trillion kilometers. So for light to travel 9.4 trillion kilometers, it will take 1 year, 1 regular year, but it has to travel at the speed of light. So if you have a ship or spaceship that travels at the speed of light, or 300,000 kilometers per second, it will take you exactly 1 light year to travel 9.4 trillion kilometers to your distance. So that's 1 light year, right? So this is our nearest star. It takes 100 light years, 946 trillion kilometers. That's insanity. That's our closest star. So even if you have a ship that travels 300 kilometers a second, or at the speed of light, it will still take 100 years to reach our closest star. And the Milky Way across is 100,000 light years. That's 946 quadrillion kilometers. Thank you very much. Let's go back to the video. And now think of that and think of an object billions of light years away, to put it in perspective. There is an article in the Webb Space Telescope website that perfectly explains the use of spectroscopy in science. I will leave the link in the description. But it basically says, we know, for example, that 91.2% of the atoms in the sun are hydrogen. We know there is water vapor in the atmosphere of WASP 39b, a distant planet 700 light years away. We know that the gas at the center of the galaxy M82 is 80 million degrees Celsius. That's 150 million degrees Fahrenheit. And that the Whirlpool galaxy is moving away from us at a rate of 460 kilometers or 285 miles every second. Astronomy articles are filled with exact compositions, temperatures, and speed of things that are too far to visit, impractical to probe, in some cases impossible to observe directly. How is it possible to get such detailed measurements like this? The answer: spectroscopy. Spectroscopy is a scientific method of studying objects and materials based on colors. The discovery of this method started by the discovery of the full electromagnetic spectrum. Remember a few minutes ago when I talked about it? The electromagnetic spectrum? Remember? Spectroscopy allows scientists to discover worlds similar to ours, with water and oxygen, along with atmospheric data, to help us identify planets for life as we know it, or simply to identify as potential worlds to host humans, in case there is a last-minute exodus from this planet. These billionaires need any reason to spend money. When I hear people talk about space exploration, I'm included in that gen pop. Their main focus is alien life. And personally, I find it a bit disappointing, as researchers around the world for centuries have provided us with great data about the universe. Data that can be dependent for the survival of humanity here on Earth and perhaps in worlds outside our own. Understanding the universe we live in, helping our survival and evolution is, in my opinion, more important than discovering or the idea of alien life. Don't get me wrong, the depiction of alien life, specifically advanced, evolved, or intelligent alien life, is a scary concept, it's a scary idea. And I'm not saying that it doesn't exist or it's not true. It's just that to this day, there is no evidence of that. But if it's true, it is definitely something to be scared about. We need to consider a spectrum of life and what intelligent life means, right? Because it could be life in bacterial form. We don't know that. It's still extraterrestrial, it's still alien life, even if it's bacteria. It's just, if it's not on Earth, it's alien to us, right? It's extraterrestrial. For now, that idea is just science fiction. The main thing I learned is that light is a tool that can detect the molecular composition of any object that absorbs and reflect light. And I want to end this video with this thought. What if we evolved with cells capable to see the entire radiation in the electromagnetic spectrum? Not just the visible light portion, but the entire spectrum. Would our evolution be different? Would we be able to interact in different dimensions? Be like godly beings, right? Or would our existence be as mundane as any other organism on planet Earth? Thank you for watching.